Hi, I'm talking about overcoming challenges of SerDes integration on SOCs. So SilabTech is a company which is focusing on high-speed SerDes IP, and over the past years, we have worked very closely with our customers to integrate our IP into their test chip. And this is basically a summary of the learnings that we have had. So this diagram shows how a SerDes looks like in an SOC. So typically an SoC would have an IO ring around it, and what I've shown here are flip chip bumps. And then there is a digital core, and I've shown an example where there are two sets of SerDes IPs located. And of course, the sizes and the bump sizes are just representative. On the right, I'm showing a real 4-channel SerDes example. This is our 28 nanometer TSMC 28 HPM SerDes. And so this includes 4 channels of receive, a PLL, and 4 channels of TX. The TX is a bit smaller than RX in area, so that's how it looks. So in an SoC, the SerDes also includes its own ESD, which integrates in the SoC IO ring. Uh, Going forward, this is how a SerDes IP looks like on the inside. You have multiple transmit lanes where the parallel data is serialized and driven out on the serial lines. In the middle, you have the PLL and the common biasing blocks. And then on the other side, you have the receive lanes. On the SoC side, we deliver a PCS soft macro and the register bank, which does the configuration of various parameters of the SerDes. And then there is the IEEE 1500. I'll cover these blocks and the integration of these blocks. So as far as integration goes, there are various checkpoints which I have labeled here. So on the SOC interface side, you have the PCS soft macro, which takes in the data from the controller or the upper layers and passes it on to the SerDes. On the DFT aspect, you could have an IEEE 1500 or a JTAG interface to test the IP. Then a SerDes is something which talks to the external world. So there are pins and there are aspects related to physical design and package design. On the physical design side, there could be aspects related to halo or keep out away from the sensitive analog portions of the SerDes. Then there are power supply related aspects to be thought of. And then there is ESD and bumps. For clocking of these IPs, so these are very high speed, very jitter sensitive IPs. So the clocking and the reference clock design for the SerDes is also one very critical aspect. So in the following slides, I'll cover these aspects one by one, and then I will show how our IP has solved these problems or tried to minimize the things which can go wrong at the SoC level. So on the SoC interface side, the SoC would have a digital interface to the SerDes. So what is very important is the accurate description of all the pins and the register views of the IP. And at a SerDes which runs at 12.5 Gbps has a very fast interface even at the parallel data level. We can slow it down to half or a quarter rate, but it still has a fast parallel interface. So the timing arcs to the SerDes from the SoC are to be looked at. And a SerDes IP typically includes a lot of analog. So there is the other aspect of the quality and functional checks. So there is this aspect of how accurately is the analog modeled. And when you go for accurate simulations, the simulations and SoC verification can be slow. So there is this trade-off of accuracy versus speed of simulation. So I'm showing how we at SilabTech develop our SerDes IP. So the blocks in green are blocks which are developed in the digital flow, and the blocks in yellow are the blocks developed in analog flow. So this IP can be built, the PHY or the SerDes can be built in an analog top flow, and this is an approach taken by quite a few companies, but we don't do that. There are several problems associated with this flow, and most of these cause issues at SOC integration time. What we do is we wrap around the analog with a digital, and that entire top level of the IP is built in the digital flow. There are several advantages of that. So it enables the use of standard digital flow for IPQC during development. And most of the times that is what is being done at the SOC level also. In fact, it could be the same set of tools which are used for implementing the digital of the SOC. And the models and the views that are delivered to the SOC are also produced by the same tools and the same flow. And there was this aspect of high-speed timing closure at the PHY and SOC interface. And so again, during the implementation of the IP, we constrain the SOC interface path to just consume 20% of the time, and the remaining is available to the SOC. Again, this constraining and checking with the constraints is possible because we do this IP top in the digital flow. And we have a methodology to build the IP from a specification which can be read by our internal tools. So especially the pins and the register descriptions, we provide the pins and the description, the direction, and the power domains of the pin in the form of a spreadsheet. And the IP is built using that spreadsheet. So that is the view which is shared with the customer, and that is the view which is used by our scripts to build the interface, to build the boundary scan, to build the register banks. So what is shared as documentation is exactly what gets implemented. And the other advantage of using this flow is we again can use the script-based flow for verification. So all of these aspects which are documented in the spreadsheet are verified again by scripts. So this is a specification-based top-down design flow, and basically it enables a very good quality check, and it allows us to efficiently implement what we are documenting. So on the physical design side, there can be requirements from the IP to keep out the noisy blocks, and there could be definitions of halo around the IP. So that is something that the SOC integration needs to bother about. On the power supply, on the power supply side, there are concerns about EM and IR on the power input to the SOC, or to the IP, I'm sorry. On the ESD protection side, the IP, because it talks to the external world, it has to meet the ESD guidelines and the ESD spec. And once that integration of ESD cell is done, we need to have the integration checked out, especially the resistance of the ESD paths. And then there is this other aspect of the bump and pad placement. So these are very high frequency IPs which are very sensitive to parasitics. So any bumps being placed over the IP can cause parasitics to the circuits underneath. So that is something that needs to be taken care of. So the way we build our IP is we take care of all the sensitive circuits by placement, and we surround them with a halo internally, and we minimize the keep out regions that the SOC needs to take care of. The power grids are built in, and static and dynamic IR drop models are provided to the SOC. So this is again a very important aspect. Although the IP has a lot of digital, we do not leave the power grids to the SOC. We build the power grid on our own over our IP, and the reason we do that is, I'm sorry. So the reason we do that is because the timing analysis needs to be done with the power grid being present. So our ST is closed with that, and the power pins are always available at the edge of the IP. So this is a snapshot from our integration spec where we show how the power grid is to be hooked up, and how we require all the pins to be hooked up. Again, the SerDes IP itself includes ESD protection. If we validate the IP on a test chip, we also do ESD testing on that IP. And to check the ESD integration on our IP, we have our internal flows to check the resistance of the paths and the ESD parameters. And the IP itself includes bumps and the routings completely inside the hard macro. So the SOC does not need to place the bumps and route them. So this takes care of two things. So the SOC need not bother about what parasitics are critical to the SerDes, and from the IP quality point of view also, uh, we have a known presence of the bump and that bump routing, and we extract and simulate that. So next comes the aspect of package design. So the SerDes routings, they are extremely parasitic critical. So these routings need to meet various specs. Mostly they are insertion loss, return loss, and skew related requirements. And many times there are very few layers in the package. Typically it's just 4 layers. So a lot of routings are packed in a very small space with very critical routing resource. And a similar situation exists on power supply and ground planes. The package needs to provide very low resistance and inductance to the power supply, and with fewer layers and many channels of a SerDes packed together, so there is a scarce routing resource. There is the other aspect of sharing multiple BGA balls. So if you have multiple lanes of a SerDes, each one cannot get its isolated power supply. You need to share the power supply bumps to minimize the pin count of the chip. So that aspect needs to be taken care of. So in our IP design flow, we start working with the packaging team of the SOC very early in the cycle. And the way we do that is we provide the IP port S parameters as the S2P files for the SOC to directly simulate and verify that. So the SOC packaging team can directly start working with the standard, and they know how the termination of our IP looks like, and all they have to do is simulate their part of the design with the standard spec. And this is a snapshot from our integration spec where we illustrate how multiple IPs can share the package balls. And what we do is we specify the parasitic constraints on these paths that the packaging designer needs to meet, and what is the limit on number of IPs that can share the balls. So this is done early on. And regarding crosstalk, so our IP inherently has all TX channels on one side, all receive channels on one side. So this inherently minimizes the crosstalk at the near end. So that's the NEXT near end crosstalk. On the DFT integration, so the IP can have a JTAG interface or a IEEE 1500 interface for DFT. And many times the SOC can use the other interface, so there is a mismatch possible on there. Then because the SerDes has pins on external to the chip, so integration of the AC JTAG and DC JTAG has to be done. Then there is this aspect of testing the analog content in the SerDes. So typically analog requires trim or even analog quantities being measured, and that amounts to test time, so that is a concern. And then there is a concern of coverage, meeting coverage goals with the analog present. So I'm outlining the DFT architecture of our SerDes. So we use the 8-pin IEEE 1500 DFT interface, and this is something that can be easily plugged into a JTAG tap at SOC level, and there are ways we can do that. And the entire APB register bank of the IP is accessible again via P1500. So in any of the test mode, the IP configuration is possible through IEEE 1500 itself. So there is a bridge included from IEEE 1500 to APB inside the IP. And then the digital part of the SerDes supports a plug and play scan test. So the test interface of the IP simply needs to be mapped to a GPIO, and the wiggle patterns that we provide can be run on the tester. And as far as the analog testing and the test time goes, so all of our analog is tested with BIST. So it allows using a low-cost tester. No analog quantity has to be measured on the tester in production. This reduces the test time, and for enabling this, we also deliver the test benches to exercise each of the BIST modes. And then the IP itself supports the AC and DC JTAG, which is the boundary scan. So we deliver the boundary scan description language pre-validated view. And that particular interface is proven with standard JTAG tab controllers. So on the clocking aspect of the SerDes, so there are two main things. There is the reference clock for the PLL and the routing of high frequency clocks. So the reference clock from the PLL needs to be a very clean clock for most of the interfaces. In fact, interfaces like PCI go on to specify the jitter on that clock as well. And then there are concerns related to the routing delay and jitter and the coupling. And pretty much the same concerns are present for the high frequency clocks which exist in the SerDes. So the way this is taken care of is by integrating a reference clock buffer inside the SerDes IP. So this is typically done for most of the PCI Express interfaces where there is a 100 megahertz clock to be taken in from outside. But this can also be done for several other standards. So this reference clock buffer is contained inside the SerDes, and this routing is contained inside the SerDes. So this is pre-validated and simulated by us. On the high frequency clock which comes out of the PLL, so this clock is also contained within the SerDes and it connects to the channels by abutment. So this is something that the SOC does not need to route. And then there's this aspect of the timing at the interface from the digital side for the SOC STA. So to enable that, our IP internal clock tree is available in the .lib itself. So this is a big table. This is just a summary of all the different views which are delivered with our IP to enable the integration of the SOC. So I'll just quickly cover some of them. So the specification is something that we deliver in the document and the spreadsheet form. On the physical model side, we also deliver the on the physical model side, the initial extracted timing model is also generated from the spreadsheet and delivered. On the stuccat and DFT patterns, we deliver the wiggle files which can be run directly on the tester. And for the analog test, we develop the test bench and share it with the SOC team. So in summary, so SerDes integration involves a lot of aspects like we have seen, and some of these aspects require early planning and co-design, like the package design, for example. And DFT and timing are the other aspects which depend on the IP development methodology. So I've just shared some of the features and our methodology that enables us to ease the integration at SOC level. Yeah, so that's the end of my slides. I can take any questions.
Any questions for Ravi? Well, you can find SilabTech's IP catalog on ChipEstimate.com.
What's the typical BGA size for the package?
For our IP or the SOC?
The SOC for the SerDes?
The BGA pitch, are you asking about?
Yeah.
Yeah, so the BGA pitch is typically 0.65, and we go to lower pitch also, but then it is limited by crosstalk concerns.
Any other questions? Oh, fantastic. Thank you so much, Ravi.